Hey everyone, welcome back to The Explainer. Today, we're tearing down the surface-level explanations of why electric vehicles lose range in the winter. We aren't just going to sit here and tell you that batteries don't like the cold. Instead, we're taking a rigorous, documentary-style journey straight into the molecular reality of the battery cell itself. We are going to explore the exact physical and electrochemical bottlenecks that literally drain your capacity when those temperatures drop.
So, why does cold weather actually destroy EV range? This is the central question we're unpacking today. If you've ever driven an EV in freezing conditions, you've definitely watched your expected range just plummet. But what is physically happening inside that battery pack to cause such a dramatic drop? Well, we're going to zoom all the way down to the atomic level to see exactly how the laws of physics are working against your vehicle.
Okay, let's dive into this, because frankly, the reality is stark. If you've ever stood shivering at a charging station, suddenly realizing your planned road trip is pretty much impossible, you know exactly how frustrating this is. In severe cold, specifically around -20°C, an electric vehicle can lose up to 50% of its available capacity. Think about that. That is half of your driving range simply vanishing into the freezing air. To understand how we lose so much energy so incredibly fast, we need to map out exactly what's failing inside the cell. Here's our roadmap for today's explainer. We'll start with the winter range problem, then look at viscosity and the Stokes-Einstein Equation, move on to resistance and voltage sag, tackle the lithium plating threat, compare NCA and LFP chemistries, and finally, look at engineering the thermal solution.
All right, Section 1. Viscous electrolytes and the molecular bottleneck.
To really get this, we need to shift our focus down to the microscopic liquid environment inside the battery, the electrolyte. Think of this as the superhighway that lithium ions travel on to deliver power. Now, what's really interesting about this slide is that the data reveals a totally counterintuitive truth. You might naturally think that in the cold, ions lose thermal energy and just clump together, a process called ion pairing, leaving you with fewer free charge carriers. But a rigorous molecular dynamics simulation proves otherwise. Look at the data here. As the temperature drops to -20°C, the fraction of free lithium ions actually increases, because the cold increases the solvent's dielectric constant. It actually helps keep those ions separated. So a lack of free ions? Not the culprit. The true bottleneck is something else entirely.
The real villain here is perfectly described by the Stokes-Einstein Equation. While the ions are technically free, they are physically trapped. As temperatures plunge, the liquid electrolyte essentially transforms into molasses. The physical viscosity of the solvent increases drastically, which heavily limits the self-diffusion of the solvent molecules. So the lithium ions are perfectly ready to move, but they're trying to swim through a rapidly thickening fluid. The ionic conductivity crashes, not because the ions are paired up, but because they are physically bottlenecked by this cold, highly viscous solvent.
Moving right along to Section 2, resistance and voltage, the electrochemical toll.
Now, this microscopic sluggishness we just talked about doesn't just stay at the atomic level. It translates into a massive electrochemical toll on the whole battery. Just look at the exponential curve on this graph. This is the visual proof of the penalty we pay for cold weather. The internal resistance at the electrodes, the solid electrolyte interface, and the electrolyte itself just skyrockets. Testing shows that at -20°C, internal resistance surges to 5 times its normal level compared to room temperature. It's literally like trying to force a massive amount of water through a tiny straw that's shrinking by the minute, which leads to huge I²R energy losses just from pushing that current through.
And it's not just the travel through the electrolyte that gets harder. The actual chemical handoff at the end of the journey becomes agonizingly slow. Dictated by the Arrhenius Equation, cold temperatures demand a much higher activation energy for these electrochemical reactions. This violently slows down the vital charge transfer velocity right at the electrode interfaces. The lithium ions are physically struggling to get out of that liquid electrolyte and embed themselves into the solid structure of the electrode.
And this brilliantly illustrates the real-world consequence of all that resistance: massive voltage sag. Notice the huge drop in the curves at 0 and -20°C compared to that optimal 30° baseline. When your vehicle demands power, that high internal resistance causes the voltage to heavily dip under load. Because of this, the battery hits its low voltage cutoff limit way earlier than it normally would, effectively hiding vast amounts of capacity. The energy is still physically sitting right there in the cells, but the voltage sag absolutely steals your ability to access it.
Section 3. The lithium plating threat and dangerous charging.
We've seen how the cold robs you of power, but now we need to look at a much more severe issue. Low temperatures introduce some really dangerous mechanical risks to the battery architecture itself.
This brings us to a critical failure mode known as lithium plating. When charging a battery, lithium ions are supposed to smoothly intercalate or safely embed themselves into the layered structure of the graphite anode. But in the cold, because that intercalation rate is severely limited, forcing a high current into the battery causes the ions to just stack up at the border. Unable to penetrate the anode, they irreversibly deposit as pure metallic lithium right on the surface.
The cascading effects of this lithium plating are devastating. It causes an immediate loss of active material and traps inactive lithium ions, leading to permanent capacity fade. In fact, operating aggressively in the cold results in roughly 4 times higher cycle life degradation. But wait, it gets worse. This metallic lithium can accumulate into sharp, needle-like structures called dendrites. If a dendrite grows large enough to actually pierce the separator, it causes a catastrophic internal short circuit. This right here is exactly why your EV artificially restricts fast charging and turns off regenerative braking on cold mornings. It's protecting itself.
On to Section 4, comparing NCA and LFP chemistry in chemical resilience.
So, the crucial point is, physics presents a formidable challenge, but not all batteries suffer equally. Nickel-cobalt-aluminum, or NCA cathodes, show superior low-temperature charging dynamics. They maintain longer constant current charging phases, thanks to their specific material structure. On the flip side, lithium iron phosphate, or LFP cells, struggle a lot more. Studies show that LFP charge transfer resistance is a whopping 3 times higher at -20 degrees Celsius compared to room temp. Plus, because LFP has a lower overall energy density, it actually has the highest thermal mass per energy charged. Simply put, it is way harder and takes a lot more energy to warm up a heavy LFP pack.
Finally, Section 5, engineering the thermal solution and fighting physics.
Let's move to and see how this builds into practical countermeasures. Knowing that cold fundamentally limits ion diffusion and just spikes internal resistance, automakers mandate that these vehicles absolutely must operate anywhere from -30 to +60 degrees Celsius. And since we can't break the laws of physics, engineers fight them with heat. Vehicles implement complex active thermal management systems, like highly efficient heat pumps. They literally use energy from the battery itself to generate heat, often sacrificing overall power output just to warm up those cells. By preconditioning and preheating the pack on your way to a charger, the system artificially lowers the electrolyte viscosity and internal resistance. This safely enables higher initial charging power without risking that dangerous lithium plating we talked about. Ultimately, EVs have to actively spend their own energy to save the battery.
Which leaves us with a totally fascinating challenge for the future. We've seen that the primary bottleneck is solvent viscosity. So the ultimate question is this: can material scientists engineer novel, low-viscosity electrolyte formulations that actually break the Stokes-Einstein limit in the freezing cold without boiling away or causing safety hazards in the blistering heat of the summer? It's a delicate balancing act of chemistry, and it's absolutely going to define the next generation of electric vehicles. Just a little something to think about the next time you precondition your car on a frosty morning. Thanks so much for joining us on this deep dive.